Good evening. I am an experienced F-sharp developer at Ciklum. I'm here for 2 years, almost 2 years now, and before that I have like almost 10 years experience with functional programming and F-sharp. And today I want to talk about immutable data structures because it's core feature of every functional programming language, and it slowly gains popularity also in other languages like C# or Java. So what's the immutable data? It's one of the definition is it's a very object that cannot be changed after it's created. That can give us quite a few advantages. Mutation is common source of bugs. I'm quite sure you see some of them in your past. When you have immutable data, it's quite a lot easier to reason about your code and debugging it, because when you pass some data to your function, you don't need to look inside the function. You never your object is never changed. Your value is still the same, and it's allow a lot of easier refactoring. And maybe most importantly, immutable data are thread safe. There is no possible race condition. We can look, and there is also something like bonus. When you have immutable data, you can easily record all history and go back, and it's work out of the box. We can look at some example. It's maybe a little stupid example, but for example sake, it's correct. Let's see, we have some account object and then have money that's mutable, and we have function that decrease some money for some amount with some method pay. There's multiple problems. We don't record the history, and maybe most importantly, there is race condition in the pay, and if we run the pay method in parallel, we can get anything between 0 and 900 values for it. If we use immutable data for this, we don't get like for free all race conditions solved, but advantages is that we get always the same result. Here, the result depends on how quickly the method run on different threads. Just quite common myth that when you have immutable data, the only way how to do it is just freeze your values, and when you have, for example, array, and you want to create you want to update one value, you need to copy all the data and just change the one value. That's not true, and in this talk I will show you what common techniques are used for immutable data structures. The trick is that we create our structure with links, and we share the parts that not changed in our updates. The most common data structure is linked list, and for example in F# is called just list. There is few common notation in F#. I the first is more common, but I also included the second one because it quite nicely shows what's happening inside. Linked list is always created as one item that link to the rest of the list. And on the end of the list, there is special object that have meaning of an empty list. This way, we can share the part. And for example, if we created new list by adding new item at the beginning of the previous list, we reuse this list into two objects. That also means we can also only change or update this list by adding some values on the top of it. So if we want to do some change, create some new value with a new name with change values, we actually can't change it because it's immutable structure. But what we do is we take the reference to this sublist and add the new value with a different value and create an updated list. What's interesting about lists is that I'm sure you know about the tool Git, and when you look at it, how Git works, it's actually just the same technique applied differently. The commits are items in the lists, and the different branches are actually just differently named references to some lists. So Git is basically a bunch of immutable structure, bunch of lists with some named references on few other features. To show that immutable data structure is not so slow that is often people say it's so slow, I did some simple benchmark. Here we create some list and filter out half of it, and then some the results. And there is the same thing with mutable data. You can see that immutable is slower. Yes, this is ratio. It means how much this implementation is slower than this one, and also how many more memory it allocates. You can see it's slower, but it's nothing something dramatic. But some notes about benchmarks. Benchmarks are very hard to write correctly and very time consuming. It's very easy to make mistakes, and it's hard to figure it out because it's not so easy to see them just because something is slower. There's always ways to make some benchmark faster. You can start using some tricks, convert it to assembly, and so on. So often benchmark starts to deteriorate to some assembly tricks competition. So it's better to see as benchmark as only indication how good or bad it is, not to look too closely to exact numbers. And all benchmarks are wrong. You can always find something that's wrong on benchmark, or they are measuring the wrong thing. Okay, let's look at another important data structure, that it's set, because maybe set is not that used, that, for example, dictionary, but for immutable data structures design, the dictionary-like immutable data structure are based on set. Set is an ordered set of values. It's implemented typically like balanced tree. What does that mean? We have the values ordered in this way, and it's similar to binary search tree. That means we have some value on the top, and on the left we have values that are smaller, and on the right hand we have larger values. And that's how we go on that. And balance means that we have quite nicely, we have similar number of items in each branch. That's basically what's mean. Technically, it means that the depth, that means number of nodes to the end, is not bigger. Difference between them, it's not bigger than 1. We can look how it's look like if we try to add some item into this tree. We see that 35 was added, and now the structure was rebalanced, so it doesn't look like too much deep on one side. This is done because every operation that we do on this structure is depending on the depth, how much to bottom we need to go. So when we do this rebalancing, we ensure that all operations will be performant. How the structure sharing looks like in this structure? When we add the item, like in previous slide, we change these yellow nodes, and here is our new item, but everything else is unchanged. So this whole subtree can be shared with old value. We can look how it's look like when we creating a brand new set and adding new values, and how the rebalancing work. You can also see that every time we adding new value, we first found the position where the value should be added, and then edit, and then ensure that balancing rules are satisfied, and if not, do some rebalancing. So, and also some benchmark on set, it's quite interesting, because when we ask if some item is inside the set, the results is quite the same for immutable and mutable version. But if we also create new structure, it's different story. It's actually because the rebalancing I was showing you, this is the extra work we need to pay for the immutable data structure. So from this, we can say that when we working with immutable data structure, it's better to avoid too much creation of new objects, and it's better to work in iterative way as much as possible, just adding only what we need to add at the time. Now let's look at the map. Map is immutable structure that is similar to dictionary. And internally it works like set, but for each key or each node we assign value, and that this way we get key value pairs. And sharing works similar way in our previous example. It's quite the same, but with the new value we add also some value. We added the key and the value, and the internal structure is based on keys. The important thing here is also that values are linked by reference to the key. That means if we have some big object here in values, then these objects are shared, and if we changing structure of keys, for example, changing values of keys only, we reuse the memory of values, and it's not a memory expensive operation. And also some benchmark. It's very similar to set. It's not surprising. Maybe there is interesting that creating of map is not, there is not so big difference, probably because we, in both cases, we need to do the work for creating values. So it's closer. Okay, that's almost all I have prepared, but we have some time left. So I have some bonus slides. So records, it's core structure in probably every functional programming language. It's something like class, but with immutable data. What's important about it is that also in record, the fields are just references. When you update, you create new values with some changes. You just create new value here, and for other fields, you just copy the reference. No big data is allocated. So in a sense, record is most simple immutable data structure. And also, this is like specific for .NET, but it's common also in other languages, that for immutable data structures to work correctly, we don't need only equality, how it's common in mutable data structures. For example, in dictionary, it's enough to have equality for object to be used as key. But because we use these trees and we need to know what's more, what's bigger, we need to be able to compare it. And also, it's quite common when working with immutability that we create some object that actually is the same thing. So for that reason, in F#, the basic or all objects you create from these structures have defined comparison by default. And that's good for working with these structures because, as I said, it can quite easily happen. You have the same thing, but it's different object with different references. And this is thing that's quite common, and I think you can find it in every functional programming language. Okay, that's all from me.